Hello, I am Naonori Sugiyama at NAOJ. This is an explanatory video of my recently submitted paper. First test of the consistency relation for the large-scale structure using the anisotropic three-point correlation function of BOSS DR12 galaxies. It's only about 10 minutes long, so I would be very happy if you could watch it all the way through. Since this is the first time I have tried to make a video like this, I am experimenting with a few things. One of them is that I have prepared videos of me speaking in different languages using automatic translation software and automatic speech reading software. If you have trouble understanding my distinctive English, you can watch the videos in your native language, including English. However, I do not guarantee the accuracy of the translation. The links are posted in the comment section. I made this video for 4 reasons. The first is purely to promote my work. Many people may not read my papers, but they may watch my videos. The second reason is that I want to change the situation where the only way to associate a paper with the author's face is at conferences and seminars. I want people to remember my face more. Third, I want people to use my videos in archive seminars. Many universities hold archive seminars every day, but isn't it hard to summarize a paper you just read? In such cases, I, as a first author, will give you an overview of the paper beforehand. Then, all you have to do is play this video at the archive seminar. Finally, I prefer to keep scientific discussions as open as possible. Therefore, if you agree with my opinion, I would appreciate if you could post it in the comment section of YouTube in case of scientific questions, so that others can see it. In this way, perhaps new projects may be born from such an open discussion. Of course, you can also send me an email to the address below directly. Are you ready? Please have a good time. Thank you. In this talk, I report on the first observational test of the consistency relation for the large-scale structure of the universe using the anisotropic three-point correlation function of galaxies, the anisotropic 3PCF. This work has 3 phases. First, we directly constrain cosmological nonlinear gravitational effects from 3PCF measurements. Then, as a result, we provide an observational test of the so-called consistency relation. This relation is known to be satisfied in a large theoretical framework for the large-scale structure. Finally, as some examples of violation and non-violation of the consistency relation, we constrain modified gravity theory models. This result has already been summarized in a separate paper. This research is motivated by a desire to deal with information that can only be obtained from 3-point statistics measured from spectroscopic galaxy data. One of these is a nonlinear gravitational effect. While the cosmic microwave background radiation, CMB, can be described mainly by linear theory, nonlinear gravitational signals can only be detected by observations of the large-scale structure after the universe has sufficiently evolved. To theoretically describe the nonlinear effect of the galaxy distribution, the galaxy density fluctuation is decomposed into first, second, third, fourth, fifth orders, and so on in perturbation theory. The first order means the linear theory, and higher orders represent nonlinear effects. In the case of the 2-point statistics, the linear term appears as the leading order term, and the nonlinear effect appears as the next leading order term. Furthermore, the nonlinear effect appears as a mixture of second-order and third-order fluctuations. On the other hand, in the case of the three-point statistics, the leading order term appears from the second-order fluctuation. It allows us to measure the nonlinear effect more directly. This is the reason why we use the three-point correlation function for this work. The second-order density fluctuation is decomposed into three components. The first is a nonlinear growth term, which is the square of the linear fluctuation. The second is a shift term described by the product of the displacement vector and the first-order spatial derivative of the density fluctuation. The final term is a tidal term, which consists of the second-order spatial derivatives. In addition, the redshift space distortion effect can provide information about the galaxy velocity field as well as the galaxy density field. This effect causes the observed redshift to deviate from its true value by the peculiar velocity of the galaxy due to the Doppler effect. As a result, the observed galaxy density field becomes anisotropic along the line of sight direction. Therefore, in order to extract the nonlinear velocity information, it is necessary to evaluate the anisotropic component of the 3PCF induced by the redshift space distortion. This anisotropic 3PCF is essentially important for testing the consistency relation. We will explain that later. In the case of dark matter in general relativity, the coefficients of these nonlinear terms can be calculated analytically like these values. In this work, we assume a case beyond the simplest case of dark matter in general relativity. Then, we constrain the nonlinear term coefficients of the density and velocity fields as free parameters using the anisotropic 3PCF. The definition of this parameterization is presented in equation 3 of this paper. We summarize what nonlinear parameters of interest take on values for various models in section 2.3. The marked models violate the consistency relation. Please refer to the paper for details on each. Now, we give an explanation of the consistency relation for the large-scale structure of the universe. First, consider the Fourier transform of the 3PCF, the bispectrum, computed from the density fields at three different redshifts. Then, we compute the squeeze limit of the bispectrum, where one wave number Q1 is sufficiently smaller than the other wave numbers. It is known that the shape of the squeeze limit bispectrum is uniquely determined within a fairly wide range of theoretical frameworks. In other words, the squeeze limit in the bispectrum corresponds to the operation of extracting only the shift terms. The consistency relation means that the coefficients of these shift terms are 1. When the Fs and Gs parameters are 1, the squeeze limit bispectrum is described as the difference between displacement vectors at different redshifts. This is the consistency relation for the large-scale structure of the universe. On the other hand, if Fs and Gs are not 1, the consistency relation is broken. But please note that since both Fs and Gs are always degenerate with sigma 8, we cannot directly constrain Fs and sigma s in Gs. In order to eliminate the sigma 8 dependence, we define the range of Gs sigma 8 to Fs sigma 8 as Es. We constrain this Es parameter. In order to determine the coefficient of the shift term without sigma 8 dependence, we need information about the nonlinearity of the two fields. They are the density field and the velocity field. This is the reason why we use the anisotropic 3PCF in this work to test the consistency relation. By the way, this ES parameter was initially proposed in the paper by Yamauchi and Sugiyama as of 2021 to constrain modified gravity theories. If this ES parameter is not 1, the consistency relation can be considered broken. This is a sufficient condition, not a necessary condition. It is possible for Fs and Gs to be equal to each other and not equal to 1. Therefore, even if the consistency relation is broken, it does not necessarily mean that Es is always unequal to 1. Still, there are some problems to be solved. In actual observations, it is challenging to measure correlators between galaxy density fluctuations at different redshifts. This is because the galaxy density fields at different redshifts are so far apart in the radial direction that they cannot be correlated. Therefore, it is common to measure the correlators of the galaxy density fields at equal time so that Z1 equals Z2 equals Z3. In this case, the squeeze limit bispectrum is 0 because it is described by the difference in the displacement vectors at different redshifts. Even if Fs and Gs are not 1, the squeeze limit of the equal time bispectrum is also 0 due to the symmetry of the K1 and K2 dependence of the bispectrum. Therefore, we propose to constrain the ES parameter from the equal time 3 PCF without taking the squeeze limit. In this case, we simultaneously vary the nonlinear parameters so that the result holds in as general a situation as possible. This is the measurement result. This study uses the so-called Troposh decomposition of the 3PCF, then use of the first two components of each of the monopoles and quadrupoles of the 3PCF. The 3PCF depends on two variables, R1 and R2, but for simplicity, only the case R1 equals R2 is plotted in this figure. Please be assured that the actual data analysis also uses the cases where R1 and R2 are different. For example, the BAO signal can be seen in the monopole component. The measurement of the quadrupole component also agrees with the theoretical prediction. This is a constraint result for ES. By combining all four BOSS samples, we constrain the ES parameter. ES is consistent is 1 within statistical errors. Therefore, the consistency relation is satisfied in this analysis. Finally, we have provided constraint results not only for ES but also for the other nonlinear parameters in appendix. These results should be used to constrain the specific model given in section 2.3. This marks the end of my presentation. I will now take the next 5 minutes to discuss my research accomplishments thus far. I kindly request that you continue to engage with my talk if possible. However, if you are unable to do so, please feel free to stop watching this video. If you are still following me, I would like to express my deepest appreciation for your continued attention. Thank you very much. Today, I have authored 4 publications focused on the anisotropic 3-point correlation function culminating in the present study. In the first paper, we suggested decomposing the bispectrum and 3-point correlation function using a basis known as tripolar spherical harmonics. This basis is composed of the product of 3 individual spherical harmonics. The Troposh decomposition method offers several benefits. First, it enables the quick analysis of galaxy data using the fast Fourier transform. Second, it permits complete window function corrections. Last, its correction to prior research is evident. For instance, it can efficiently manage non-zero M modes in the widely used Scotch-Mallows decomposition method while incorporating window function corrections. We applied this triple decomposition approach to obtain, for the first time, a quadrupole bispectrum signal from both galaxy data at the 14 sigma level. In the second paper, we used perturbation theory to calculate the bispectrum covariance matrix and evaluate its key features. This investigation is crucial to understanding the statistical errors associated with the bispectrum prior to conducting cosmological data analysis. In this work, we computed for the first time the covariance matrix of the anisotropic bispectrum, incorporating up to 6-point statistics. The main properties of the bispectrum covariance matrices presented in this paper are as follows. First, the non-Gaussian term plays a crucial role in the bispectrum covariance matrix even at large scales. Second, the short noise term is significant within the non-Gaussian term. Third, the non-Gaussian term has a substantial impact, reducing the cumulative signal-to-noise ratio of the bispectrum by a factor of 3 over 4. These results suggest that the simplest Gaussian error should not be employed in the cosmological analysis of higher-order statistics. Based on these findings, we have demonstrated in a collaborative paper that removing the non-Gaussian terms from the bispectrum covariance matrix through the reconstruction method is an effective approach for constraining primordial non-Gaussianities. In the third paper, we developed a method for cosmological analysis of anisotropic 3-point correlation functions. For this purpose, we proposed a bispectrum model to describe the nonlinear damping of baryon acoustic oscillations. This model can be achieved by separating the linear path spectrum into oscillatory and non-oscillatory components. We conducted an anisotropic 3PCF analysis on the patchy Bock data. Our theoretical model accurately describes the nonlinear decay of the BAO signal. Moreover, we found that the quadrupole component of the 3PCF improves the bubble parameter constraint by approximately 30% to 40%. Since the current analysis was carried out using mock simulation data, a similar investigation should be performed on real galaxy data in future works. In the fourth paper, we present a concrete example of violating the consistency relation for the large-scale structure. We do this by constraining a modified gravity theoretical model called the Dorso theory using actual galaxy data. In this case, only 3 of the 6 nonlinear parameters possess physical significance. 2 parameters, ES and ET, have been constructed to eliminate the sigma 8 dependence. Furthermore, to combine galaxy samples from different redshifts, we parameterize the time evolution of ES and ET as powers of omega m, and constrain the exponents xs and xt that appear in them. For the lambda CDM model, xs equals 0 and xt equals 15 over 1144. Hence, our results are consistent with the lambda CDM model. In addition to studying the 3-point statistics of galaxies, I have previously constrained the statistical non-anisotropy of the universe by decomposing the 2-point statistics of galaxies using bipolar spherical harmonics. As far as I am aware, this is the only research that has investigated the statistical anisotropy of the universe using spectroscopic galaxy data. I anticipate that forthcoming galaxy survey data will enable us to surpass the constraints presented by the CMB. Finally, I have also measured the pairwise velocity per spectrum in Fourier space through the kinematic Sunyaev Zeldovich effect. I have also measured the distribution of the optimal depth around the galaxy, which appears as a proportionality coefficient. To my knowledge, this work is the only topological analysis of the KC effect in Fourier space. I hope you found my talk fascinating. I have measured various cosmological statistics and performed cosmological analysis of each. If you are interested in my past research, please feel free to contact me. I'm always open to collaboration opportunities. Thank you for your kind attention. Thank you.